Hello and welcome. Today I'm going to be looking at the Section B of 2021 Special Maths Exam 2. This exam is an absolute weapon and should be illegal to use, but the fact that VCAA used it on the Special Kids means that I have to go through it. So let's get right into it. So looking at question 1, let f of x be that function. Express f of x in that form where a, b and c are real constants. Okay, so we're going to have a constant at the front chilling by itself and then a fraction like that. So what I'm going to do is first I'm going to define it. Oops, I forgot to define. Let's actually go to the front. Define f of x to equal our fraction, which was, I believe, 2x. This will be useful for us down the track if we have to sketch it and all that. So we have x plus 5. And on the denominator, I believe it was x minus 1. And x plus 2. Okay, so what I would do is just go to algebra, expand, and then go f of x. Okay, gives us that. So we have a plus 2, which is a good sign, because remember we wanted a constant at the front. But now what I'm going to do is actually factor this part. Okay, and that leaves us with 5x take 11 on the top. Okay, so that's going to leave us with 5x take 11 with that on the denominator and plus 2. Okay, so my answer here would be 2 plus 5x. Let's write that a bit nicer. 2 plus 5x take 11 on x minus 1, x plus 2. Okay. Now it says state the equations of the graph. Okay, so the equations of the asymptote of the graph, I mean. So we have this 2 section here. That would give us the asymptote y equals 2. And looking at the denominator, we have this section here, and that gives us an asymptote at x equals 1. And we have this as well, and that gives us an asymptote at x equals negative 2. Sketch the graph of f on the set of axes below. Label the asymptotes with their equations. Basically label everything about this graph. Okay, so what I would first do is sketch the asymptotes. So let's go y equals 2. Why is it not straighten? Straighten, please. Okay, good. Y equals 2. X equals 1 and x equals negative 2. So we have 1 right here. So x equals negative 2 and x equals 1. Okay, perfect. Make sure you label them as well. We go x equals negative 2. X equals 1, y equals 2. Okay, now let's just find specific features about this graph. So first what I'm going to do is find the y-intercept and the x-intercepts, okay? That's going to help us be a bit more accurate. So let's go f of 0. That gives us 15 on 2, or 7.5. And let's solve f of x equaling 0. That gives us negative 5 or 1.5. Okay, so negative 5 is here. 1.5 would be right there. And 7.5 would be, I think 7.5 would be right there. So we go 0, 15 on 2, right? Okay, now that we know those points, what else does it want? It wants the inflection and the maximum turning point. Okay, so we can use our graph analysis to figure that out. Let's go to our graphs and sketch f of x. Okay, and let's also set our window to be exactly what they had. So I believe this was negative, was it negative 5? No, negative 10 to 10, and then, okay, so negative 10 to 10. Our lowest y value was negative 5. And their highest y value was 15. Okay, so that's what our graph should look like. Now, you can go to Analyze. Let's go to Analyze Graph, and let's do maximum. Let's do from there to like there. Okay, so it has a maximum at 4.44, 2.51. So we have 1, 2, 3, 4, 4.44, 2.51 is about there-ish, right? Right, 1, 2, 3, 4. Yep. and 2.51. It's about there, okay. So 4.44, 2.51, right? They wanted 2 decimal places. Yeah, perfect. Okay, and our inflection point. So let's go back to analyze graph. Let's click this. Okay, and there's one at 6.79, 2.45, 6.79. So that would be about there-ish. And what was the x? 2.51. No, 2.45. 2.45. So that would be about there-ish. Okay, so let's try to. What was it? 6. Why is my memory so bad? Let's go back here. 6.79, 2.45. There we go. Okay, so let's sketch this now. Let's just use a different color. Let's go like that, that, and then like that. Okay, that's like that, and then the left-hand side looks something like this. Oops, that's bad. Okay, something like that. And then our top looks like this. Okay, something like that. Okay, make sure we've labeled everything, labeled the asymptotes. I labeled the maximum turning point, which is right there. Point of inflection, right there. Their coordinates. Okay, label intercepts with the coordinate axes. We've done that. Okay, so that looks good. For what values of k will the graph have 2 asymptotes? Okay. Okay, only 2 asymptotes. So remember, when we factorize this, we had a +2, right? So that is independent of this bit here. So, okay. What I would do for this is actually just go back and redefine. Let's just go to our original and let's just go define g of x to be exactly what we had before, right? But with a minus k, was it minus or plus? Yeah, minus k. Okay, so doing the same steps, I believe it is going to be the same, but let's just expand this like we did before with the other one. Okay, and then this on the left-hand side. Yeah, see, we have the +2 there as well. And then when we factor this, let's undo that. Let's go to factor and then paste this. Paste only this section. Okay, that leaves us with all that mess there. So as you can see, we still have a +2 at the end. So that is independent of k, right? That one's there no matter what. So that means we need to do something here that's going to only let us have one asymptote. So if we look at this bottom, if we had a repeated factor, like if it was just 1 bracket squared, that would leave us with only one asymptote, right? For that fraction there. And then you'd have the +2 at the end as well. So to make these two brackets the same, k would need to be equal to what? K would need to be equal to -2. Okay? Now, what else? We could also have this bracket being the same thing as this 5, and they could cancel, leaving you with just this asymptote and the +2. So what would k need to be for those two brackets to be the same? It would need to be -5, right? And then finally, it could also cancel with this bracket, right? But to make the comparison a little bit easier, let's factor out 2 from this bracket. That would leave us with 2 at the front, x minus 3 on 2, okay? And in order to cancel these, k would need to be 3 on 2, because that would be the exact same bracket. So let's go k is equal to 3 on 2. Okay, given that the graph of g of k has more than 2 asymptotes, for what values of k will the graph of g of k have no stationary points? Okay, so what I would do here is, let's find the derivative. Oops. Let's find the derivative of our g of x. Okay, now for a stationary point, we need to solve the derivative equaling 0 for x. That's going to give us the x coordinates of where the stationary points happen. Okay, this is telling us that our stationary points would happen at either of these coordinates or either of these x values. Now, we want there to be no stationary points, right? So that means neither of these solutions need to exist. And the only way that we can have that happening is if the quantity in our square root is negative, because you can't have that as a real result. So therefore, these values wouldn't exist. So what I would do is go solve, and then I would just write whatever's beneath that square root. So I'd go negative 21 times 2 times, instead of using k, I'm just going to use x, it's the same thing, plus 7 times x, take 15. As you can see, that's the exact same thing in both of these square roots, and we want that to be less than 0, because if it's negative, neither of these solutions are going to exist. Let's solve, and that gives us x is less than negative 5 or x is greater than 3 on 2, but in this case we're using k, so we go k is less than negative 5, k is greater than 3 on 2. And it says it has more than 2 asymptotes, so it can't be either of these numbers. And looking at our restrictions, k is less than negative 5, so obviously it can't be negative 5, that's fine. K is greater than 3 on 2, it can't be 3 on 2, that's fine. And negative 2 is not within this interval, so we don't need to do any further restrictions. Okay, looking good. Okay, the polynomial p of z, and it has a bunch of letters. It does look daunting on first glance, but it says it can be written as that polynomial there, where z1 is a real number, z2 and z3 are complex numbers. State the relationship between z2 and z3. Okay, so the main piece of information here that you would need would be the fact that alpha, beta, and gamma are all real numbers, right? And we know that if we have a polynomial with all real coefficients, right, that means if there is a complex solution or a complex root, there needs to be, they are in pairs, right? So that's the complex conjugate root theorem, right? So here, if we know that this is real, that this is a complex number and this is a complex number, they need to be conjugates of each other. So here your answer would be z2 is equal to the conjugate of z3. And it doesn't matter which way you write that. You could say z3 is the conjugate of z2. Now it says determine the values of alpha, beta, and gamma given that, okay, we have a bunch of conditions. Okay, what I'm first going to use is this. Okay, but before we do that, let's say that let z2 equal a plus bi, where a and b are real numbers, right? Now what we can do is this. The fact that we know z2 and z3 are conjugates, we can go and actually work this out. So let's go the absolute value of z2, which we just defined, plus z3. And we know that z3 is going to be the conjugate of it, is equal to 0, right? Now expanding this inside or collecting the terms, we get 2a is equal to 0. And this leaves us with a is equal to 0. So that means our z2 and z3 are purely complex. Now using this next piece of information here, we can go z2 takes z3. So remember z2 is going to be a plus bi. Take z3, and z3 is the conjugate. So here we get the a's cancelling, that was 0 to begin with anyway, and then we get 2bi. So this means that 2b is equal to 6, so plus or minus 6, and then b is equal to 3. So, and the fact that we know they're conjugates, that means that z2 is 3i, and let's just write that, z2 is 3i, z3 is negative 3i. Okay, that's helpful for us. Now, what we can do is, let's actually use this form, because that would be helpful as well. And we need to pair that with this piece of information as well. So that says that when we sub in 2, we get negative 13. So we can go negative 13 is equal to 2 minus Z1, 2 minus Z2, which we just found to be 3i, and 2 minus Z3, which we found to just be negative 3i. So we have plus 3i. Okay? Now what we can do is actually go on the CAS and solve what Z2 is, or Z1 is, and that will get us closer to our solution. So let's go onto the calculator. Let's go solve. And let's go negative 13 is equal to our bracket, which was 2 take Z1, I'm just going to call it X. Our next bracket was 2 minus 3i. And then our last bracket was 2 plus 3i. And we want to solve for x. Okay, x is equal to 3. So this tells us that Z1 is equal to 3. So now that we know what all of those Z1s are, or all of the Zs are, we can actually just write our polynomial as in this form. We can go P of Z is equal to Z minus Z1, which we just found to be 3, Z minus Z2, which we just found to be 3i, and then Z minus Z3, which we found to be negative 3i, so we plus 3i. Okay, so now that we have that, all I'm going to do now is go on the calculator and expand that, and that should give us a polynomial in that original form. So let's go here. And it is similar to what we wrote here. So I'm literally just going to copy this, paste that, and what was at the front? It was Z minus 3. Oh no, I'm bad. I got to replace the 2's as well. Okay, expand. Okay, so that's what it gives us, and that looks fairly reasonable. And now all we need to do is compare our Greek letters to each of those coefficients, and we should get their values. So let's go back to our exam, and just comparing it, z cubed, yep, it looks about that form. So we can say that alpha is equal to whatever was at the front. It was negative 3, I believe. Yeah, negative 3. So alpha is equal to negative 3. Beta is equal to whatever was in front of that, 9. And gamma is equal to negative 27. So those would be my answers. Okay? Okay, next. Consider the point root 3 plus I. So that would be right there, right? Because if we drew a triangle and we had root 3 and 1, right? Tan of theta, whatever angle that would be equal to 1 on root 3. And that's going to be 30 degrees, right? And these are all 30-degree segments, right? So that's where that would be. And it says sketch the ray given by that on the Argand diagram below. So basically, you have a ray, it's been translated to the right up to this point, and it has an argument of 5 pi and 6. So 5 pi and 6, right? We agreed that all of these segments are 30 degrees, right? So pi on 6 by itself. So all we need to do is 2 pi and 6, 3 pi and 6, 4 pi and 6, 5 pi and 6, right? So 5 pi and 6 is this line. Okay, and our original ray with no translation would actually go in this direction, right? But it has been translated up to this point right there, okay? So all I'm going to do is pick this up and bring it to that point. Okay? Nicely right there. Bring our arrowhead as well. Okay. That's nice 2 marks. Alright, next part. The ray intersects the circle, okay, dividing it into a major and a minor segment. Sketch the circle on the Argand diagram. So, this circle has a radius of 1, and it's been moved 3i upwards, okay? So, that means it has been moved up to here, and has a radius of 1. So that means, hopefully this, nice, okay. Let's move this a bit. Okay, like that, right? It has a radius of 1 because it goes from 3 to 4 and 3 to 2, and it's been moved up 3i. Okay, so that's done. Find the area of the minor segment. So the minor segment would be this segment here. Okay, now how are we going to find the area of that? What I would do is, you can see that you could form a triangle from there to there, right? Now, the main issue is finding the angles in that triangle. Now, what I would say is, remember, the argument of this ray that we drew, right, was 5 pi on 6, right? 5 pi on 6. 5 pi on 6. Now, if I was to move that line right up to here, right, that whole thing would still be 5 pi on 6. 5 pi on 6. Now, we know that obviously the axis and this perpendicular line make a right angle here. So if I got this whole angle and subtracted pi on 2, or 90 degrees, that should leave me with the angle in here, right? Right, so that's what I'm going to do. So what I'm going to do is, let's get rid of this line. I'm going to have 5 pi on 6 minus pi on 2. Or you could just write that as 3 pi on 6. And that would give us 2 pi on 6 or pi on 3. Okay? So that tells us that this angle in here is pi on 3. Now, we know that this length is 1 because that's the radius of the circle. This length is also 1. So either this triangle is an isosceles triangle or it's a equilateral triangle, right? And the fact that these two lengths are the same, right, means that this angle is also pi on 3. And, you know, obviously all of the angles in a triangle add up to 180 or pi. That means this would need to be pi on 3 as well. Now, we know that that's an equilateral triangle from that point. Now, going to the actual area, what I would do is I would find the area of this whole circle, okay? And then what I would do is, actually, let's rub these out just a bit for clarity. We know that this one here is pi on 3. That's the important one. What I would do is find the area of the whole circle. Then we know that pi on 3 is 60 degrees. That is 1/6 of a circle. So if I found the whole area of the circle, I would times it or divide it by 6, times it by 1 on 6. That would give me the area of this sector, okay? And then finally, I would just subtract the area of this triangle, and that would leave me with this minor segment. Okay, so let's find the area of the whole circle. The area of the whole circle is going to be pi r squared. Pi, our radius is 1, so pi r squared leaves you just with pi, right? And we said that pi on 3 is 1/6 of the circle, so I'm going to divide our area of the whole circle by 6. That gives me the area of this sector right there. And then finally, I'm going to subtract the area of this triangle. And we know that this length is 1, this length is 1. So we can find the area of that triangle by doing half times 1 times the other one times sine of pi on 3. Okay? Now this is a formula in the formula sheet, but it can be derived. This formula just basically finds the height of the triangle and then still applies half base times height. Okay, now that we have this, we have pi on 6 minus a half. Sine of pi on 3 is root 3 on 2. So this leaves us with pi on 6 minus root 3 on 4. Okay, I'm going to use 12 as our common factor, so I'm going to multiply the left fraction by 2 on 2. And then the right fraction by 3 on 3. Okay, and this leaves us with 2 pi minus 3 root 3 on 12. Hopefully I haven't made any mistakes, but that would be my area. Units squared. Okay. A thin-walled vessel is produced by rotating the graph of y equals x cubed take 8 about the y-axis from 0 to h. Okay, all lengths are measured in centimeters. Write down a definite integral in terms of y and h for the volume of the vessel in cubic centimeters. Okay, so we're rotating about the y-axis, so we're going to integrate from 0 to h, right, our highest point. And then we have a pi at the front, because that's the formula for solid revolution. Since we're rotating about the y-axis, we're going to have x squared, and it's dy. We need to actually find what x squared is. So using this equation here, we can go y is equal to x cubed, take 8. Add the 8 to the other side. Now, how do we convert this x cubed into an x squared? We put it to the power of 2 on 3, right? Because when we expand this, these would cancel and you'd have an x squared. So if we put the right-hand side to the power of 2 on 3, we need to do the same thing to the left-hand side. Okay? And that would leave us with x squared is equal to y plus 8, all to the power of 2 on 3. So we can replace this x squared with that. Y plus 8 to the power of 2 on 3. Okay, so that would be my answer there. Hence, find an expression for the volume of the vessel in terms of h. Okay, so here what I would do is just go onto the calculator and let it do the work for me. So let's go to the calc. Let's go integral of, wait, not integral. Why would I integrate? You just, actually no, you do integrate. You need to actually work out what that integral is. So we need to go integral of 0 to h. And then we need to have, it was y plus 8. You can use any variable in here as long as in your final answer you use, as long as you keep the variable consistent. And it was to the power of 2 on 3. And it was dy. Okay, so that's our answer. So now we just go back to the exam and write that down. Nice, easy 1 mark. Okay, so here it says find the volume. So we go volume is equal to 3 times h plus 8 to the power of 5 on 3. Take 32 times pi all over, straighten. I need it to straighten. There we go. 5. Okay, that would be my answer there. Water is poured into the vessel. However, due to a crack in the base, water leaks out at a rate proportional to the square root of the depth h of water in the vessel. That is dv on dt equals that, where v is the volume of water remaining in the vessel in cubic centimeters after t minutes. Show that dh on dt is that. Okay. So to work out dh on dt, we can use dv on dt, which is what they've given us right here. But we need to multiply it by dh on dv. Okay? They would cancel and would be left with dv on, or dh on dt. Now, dv on dt has been given to us right here. But dh on dv, we need to use this. Okay? And here I've used lowercase h. Use a capital H because capital H is the whole volume, right? But even though this part here just wants it in lowercase h, you still use the same formula because integrating from 0 to any h, along that vessel will be the same formula. So here we can work out dv on dh, right? Using just our differentiation. So let's go derivative of this. Okay, so that gives us a nice and clean thing to work with. So let's go back. We know that that is this. Okay, let's copy that. Now, dv on dh is that. We want a dh on dv, so we need to actually take the reciprocal of this. Okay, perfect. So now we can just multiply it. And nice, we can get negative 4 root h on h plus 8 to the power of 2 on 3 pi. That's what they wanted us to show. Nice. Find the maximum rate in centimeters per minute at which the depth of water in the vessel decreases. Correct to 2 decimal places and find the corresponding depth in centimeters. Okay, so all I would do for this is literally just graph it and just analyze the graph. So we have negative 4 root h. I'm going to be using x's just so we can graph it easily. Negative 4 root h. And on the denominator it was, oh, what we had there. Okay, so let's go back. And on the denominator is h plus 8 to the power of 2 on 3. Oops. All multiplied by pi. Okay, so that's our graph. All I'm going to do is just graph this. Okay, and then just go to analyze minimum, because the maximum rate that it's leaking out is going to be the most negative value. Really? There has to be a minimum here somewhere. Let's do that. Okay, there it is. 24. Wait, let's just make sure one more time. Go all over. Okay, minimum, yeah, it's highlighted there. 24 and negative 0.62. 24, negative 0.62. Okay, so the corresponding depth, remember, h is our x value in that thing, and it was 24 centimeters. And our max rate was negative 0.62, but here it's actually 0.62 is the rate that you're losing in centimeters per minute. Okay. Let h equal 50 for a particular vessel. The vessel is initially full and water continues to leak out at that rate. Find the maximum rate at which water can be added in cubic centimeters per minute without the vessel overflowing. Okay, so let's take a conceptual look at this for a second. Let's go to stickies, add a blank. Okay. Let's say we have a vessel, right? Whoops, not that one. Straighten, please. Okay, and we got water in it, right? Nice and full. Now, the way that it's leaking out is different over time, right? Because it's not a constant rate that it's leaking out. But the thing is, right, even though it leaks out at different rates depending on the height, initially there's going to be a particular rate that it leaks out at. So if we put in water, right, if we put in water at that initial rate that it's leaking out, think about it. The water level won't change at all, right? Initially, if you're leaking out, for example, 2 centimeters cubed per minute, right, and you're putting in the exact same amount that's leaking out initially, right, it's not going to overflow, is it? So that would be my logic there. So the vessel is initially full and continues to leak out at that rate, right? And h is the height. So initially, the height's going to be 50. So I'd say the max rate would be 4 root 50 centimeters cubed per minute. That would be my logic there. Okay. The vessel is initially full, where h equals 50, and water leaks out at that rate. When the depth of water drops to 25 centimeters, extra water is poured in at a rate of that. Find how long it takes for the vessel to refill completely from a depth of 25 centimeters. Give your answer in minutes, correct to one decimal place. Okay. So, we can find dV on dt. That's going to be our change in volume, right? We're adding this much, so I'd have plus 40 root 2 take 4 root h, right? Because you're adding this much, so that's a plus, and you're subtracting this much because that's how much is leaking, okay? Now what I would do is actually... let's go back here. Let's go back here. dH on dt. Because we do need our equation to have time in there, right? So, ideally, we would have dH on dt here. Okay, and that's going to equal dV on dt times dH on dV. And remember, we found dH on dV right here. Okay? That was very useful to us because that applied to a vessel that had a height of 50, and it's exactly what we have here. So bringing that back here, I want dH on dt because we want, we're dealing with heights and we want time. It says how long, right? So that makes sense. So to find out dH on dt, we go dV on dt, which we just have here, times dH on dV. So divided by all our stuff here. dH on dt. Okay. Now, in order to actually take the integral of this, we need to take the reciprocal, because think about it, right? Normally when you have dy on dx, right, your equation has like x's and stuff in it. You see how these two variables are the same thing? Whereas here, we don't have t's in here, do we? So you would need to flip this so you have the h on the bottom, and that way it's the same variable as what's in the equation. So let's have dt on dh is equal to h plus 8 2/3 pi on 40 root 2 minus 4 root h. Okay, now let's take the integral of this, right? Because taking the integral of this will let us find how long it takes. Let's take the integral of this. I'm just going to copy this. And it's with respect to h. Now, let's think of it like this. If we were to integrate this, this gives us a particular time for a h that you sub in, right? So, looking back at our equation, it says initially it's full, right? At 50, yeah? So initially, no time has elapsed, has it? So if we have 50 as our upper terminal, when this is integrated, because when you integrate, you get your brackets, and you sub in your terminals. When you sub 50 in, right, since this spits out the time, it should give us 0, shouldn't it? So it's just not going to make a difference. Now, what we actually want is how long it takes to fill out. Oh, wait, let me find from 25, right? So our lower terminal should be 25, because when you sub that in after it gets integrated, that will actually give you the time. So what I'm going to do here is go into the calculator and just integrate this, and it should give us the answer. So let's go to here. We go integral from 25 to 50 of our fraction, but I'm going to use x's instead of h's. So we go x plus 8 to the power of 2 on 3. right? And it was times pi, and it was 40 times root 2, take 4 times root x dx. 31.42. One decimal place, so 31.4. Okay, so that would be my answer. Okay. Oh, this is a lot of reading. It's like specialist literacy. A car that performs stunts moves along a track as shown in the diagram below. The car accelerates from rest at point A. The car accelerates from rest at point A, is launched into the air by the ramp BO and lands on a second section of the track at or beyond point C. This section of track is inclined at 10 degrees to the horizontal. Okay, that might be useful later on. Due to a tailwind, the effect of air resistance is negligible. Point O is taken as the origin of a Cartesian coordinate system and all displacements are measured in meters. Point C has those coordinates. At point O, the speed of the car is u meters per second and it takes off at an angle of theta to the horizontal direction. After the car passes point O, it follows a trajectory where the position of the car's rear wheels relative to point O at time t seconds after passing point O is given by that, till the car lands on the second section of the track that starts at point C. Oh, that is a good amount of reading. Show that the path of the rear wheels of the car while in the air is given in Cartesian form by that. Okay. So here we have x equals that. So let's go x is equal to ut cos theta. And we also have y equals this mess. So ut sine theta take half gt squared. Okay, now let's solve for t here in this left equation. Solving for t gives us x on u cos theta is equal to t. Now we can sub that into this equation here. That gives us y is equal to u, and then we're subbing in t, which we just worked out, right? U cos theta sine theta take a half g t squared Okay, now looking at this, the u's cancel. Okay, the sine and the cos are a quotient, and that becomes tan because sine and cos is tan. So that leaves us with x tan theta. Yep, it's exactly what they want us to show. X tan theta. Take away half g x squared on u squared cos squared theta. Okay, and g is 9.8. Divide that by 2, that gives you 4.9. So I'm not going to rewrite this whole thing again. I'm just going to bring that 4.9 up here. And boom, that's what they wanted us to show. Okay. If theta equals 30 degrees, find the minimum speed in meters per second that the car must reach at point O for the rear wheels to land on the second section of track at or beyond point C. Give your answer correct to 2 decimal places. Okay. Okay, so using our equation here, we know that we want this to line up at 16,4, right? So 16,4. So we want y to be 16, right? And we want x to be 4. And we also want theta to be 30 degrees. So we want tan of 30 degrees, take 4.9 x squared. Remember, x is just 4. U squared cos squared 30 degrees. Okay, now we got this big equation here. I'm too lazy to solve it by hand, and this is a good point to just use the calculator. It won't make any mistakes. So let's switch over to our calculator. And let's go algebra solve. 16 is equal to 4 times tan 30 degrees is the same thing as pi on 6. Use radians whenever you're dealing with calculator work. I like to just be safe. Take away 4.9 times 4 squared, which is just 16, on u squared. I'm just going to call it x squared. It's easier. Times, remember it was cos 30 degrees all squared. So it was cos of pi on 6 all squared. Okay? False. What did I type incorrectly? Wait, what did I type wrong into here? Let's have a look. It's always important as well. Like, you may make mistakes when you're doing your own exam. It's important to have the skills to actually find where you messed up. Okay, so... Oh, no, that was the mistake. The x-coordinate is 16 and the y-coordinate is 4. Okay, my bad. Oops, wait, let's go back. The x-coordinate is 16 and the y-coordinate is 4. Okay. That was just me not being careful enough. Okay. People always make dumb mistakes like that. It's just important that you do check over your work later on. Okay, so we go 16 squared. That should give it a... Okay, so 17.87. So we go u is equal to 17.87 meters per second. Okay, so that would be my answer there. The ramp BO is constructed so that the angle theta can be varied. For what values of theta and u can the path of the rear wheels of the car join up smoothly with the beginning of the second section of the track at point C? Give your answer for theta in degrees, correct to the nearest degree, and give your answer for u in meters per second, correct to one decimal place. Okay, here. The first thing that strikes me is the fact that they've bolded smoothly, okay? And whenever I see smoothly, they use this in methods as well. It's related to the gradient. That means the gradient needs to be the same for any two things that are connecting, okay? And I believe that's why they've given us what this angle here is, okay? Because that lets you work out the gradient of this line right here using, right? If that's 10 degrees, this is 170 degrees, right? And you can find the gradient of that line by just doing tan of 170 degrees, okay? Now, we can differentiate this, right? That's our Cartesian equation. We can find the derivative and we can sub in 16, okay? And since it says it needs to join up smoothly, when we sub in 16, the gradient that the derivative gives us should be the exact same as the gradient of this line. Because think about it, if they're not the same gradient, that's not going to join up smoothly, is it? It's not going to be nice and smooth. It's going to be choppy if the gradients are different, okay? So that would be my first thing to compare. And then it says it needs to join up as well, obviously, so I would actually just sub in 16 and 4 again as well. So my two equations, I'm just going to call this y, right? My first equation would be find dy dx, right? Sub in, given x is equal to 16, and it should equal tan of 170, okay? And then you should also sub in 16 and set it equal to 4. Okay, so that would be all of the steps I would do there. And simultaneously solving these two as your first equation and your second equation should give you what theta and u are. Okay, so what I'm going to do now is just go onto the calculator and do that process, okay? So first, what I'm going to do is, let's just write out that equation. Okay, let's just write it out so I can copy it nice and easily later on. 4.9 times x squared on u squared. I'm actually just going to use the correct letters here, just so I don't get confused and mixed up, because it is possible to make a mistake when you're doing something this big. Okay, plus it is a 3 marker as well. It's important to be careful. Okay, so I believe I've typed that incorrectly. Now, remember what I said. I said find the derivative. And then I said you need to sub in 16, right? So I go, given x is equal to 16, right? And I want this equaling, remember, I want it equaling tan of 170. But, you know, when you're dealing with calculus and all of this mess, do everything in radians. And to convert from degrees to radians, you need to multiply by pi on 180. Okay? Just to be nice and safe. So that's our first equation, right? And then our second equation was just subbing in 16, so x is equal to 16. And then setting this equal to 4. Okay? I believe that was it, right? So let's copy this. Let's go to our solve system of equations. We want solving for u and theta. Right, so our first equation is that. That's our one dealing with the derivatives. And this is our second one dealing with the actual x and y coordinates. Okay, now the reason it's giving us multiple solutions, or it has n1, like an actual constant in there, is because, you know, our equation has cos of thetas, tan of thetas. We need to actually put a restriction for theta. So we say given theta is in between 0 and pi on 2. Because obviously that angle can't be greater than pi on 2, otherwise it's going to, like, the car's going to go backwards, right? It's going to, like, flip backwards. So our upper bound is that. Okay. That's what our answers are. Now I'm going to use the positive one because our velocity or our speed is positive. And here gives our answer in radians. To convert from radians to degrees, just multiply by 180 on pi. Okay, and that should be both of our answers if I haven't messed anything up. Okay, looks about right. Okay, let's go back. So here I would say u is equal to, what does it say? It wants it correct one decimal place, so I'd go 16.4 meters per second. And for theta, I would, what does it want it to? It wants it to the nearest degree. So I would do it to 34 degrees. Okay? The car accelerates from rest along the horizontal section of track AB, where its acceleration a meters per second squared after it has traveled s meters from point A is given by that, where v is its speed at s meters. Show that v in terms of s is given by that. Okay. Okay, so here I believe we're going to have to use one of the formulas in the formula sheet for acceleration, and I believe it is v dv dx, right? Instead of a, you can write that, is equal to 60 on v, okay? And x is the displacement, right? Here, they're saying the displacement is s. So instead of x, I'm going to write s. Okay? Now, let's divide this v across. So that's going to give me dv on ds is equal to 60 on v squared, right? Now, what we need to do is flip this, so we get ds on dv is equal to v squared on 60. Okay. Is this looking right? Have I messed anything up? Let me have a look. 60 on v dv dx, yep. Divide. Okay, it's looking okay. Now let's take the integral both sides. We get s is equal to the integral of this dv. Integrating this gives us v cubed on 180 plus c s. Okay. Initially, right, initially its velocity is 0 and its displacement is 0. So c is equal to 0. Going back up here, we get s is equal to v cubed on 180 times both sides by 180, and then take the cube root of both sides. So we get v is equal to 180 s to the power of 1/3. Okay, that would be my answer there. After the car leaves point A, it accelerates to reach a speed of 20 meters per second at point B. However, if the stunt is called off, the car immediately brakes and reduces its speed at a rate of 9 meters per second squared. It's only safe to call off the stunt if the car can come to rest at or before point B. Point W is the furthest point along the section AB at which the stunt can be called off. How far is point W from point B? Give your answer in meters correct to 1 decimal place. Okay, that is a mouthful. Oh, okay, so what I would do is, let's just draw this out first. So let's go A to B. And we've got W in there somewhere. Okay. Okay. Let's find the length of this whole track. So it tells you that he reaches a speed of 20 meters per second at point B. So let's use this piece of information here. Okay. This bit here. If we know that the velocity is 20, we can work out what s is, right? So let's just go to our calculator, just so I don't make a mistake. And let's solve 20 equaling 180 times s. I'm just going to use x. Oops. To the power of 1/3, right? 400 on 9. Okay. S is equal to 400 on 9. So this tells us that this whole length here, the whole distance that he goes, is 400 on 9 meters. Okay. Now it says, how far is point W from point B? Now we don't know actually what that is. So what I'm going to do is, let's just call that x. Okay. Let's just call that x. Right. That should be helpful. Okay. Now let's write down the information that we know. We know that at point W, it reduces its speed at a rate of 9 meters per second, right? So that means our initial velocity is equal to 9. Or not our initial velocity. Our acceleration is equal to -9, right? Our final velocity, right, at point B, it needs to actually stop before it gets there, or at there, is 0, right? The distance he travels is going to be x, right? So we go, the displacement is x. Okay. What's our initial velocity though? That is the main thing. So our initial velocity, we can actually work out our initial velocity using this equation again, right? Because we do know our displacement. We can go our velocity, right? Our initial velocity, I'm just going to call it u. Using that equation again gives us 180 times s, right? S is how far, or the displacement that the person has traveled. And the distance from here to here is going to be our whole distance minus this distance. So in that displacement section, I'm going to put 400 on 9 minus x, okay? And it's all to the power of 1/3. Now that tells me my initial velocity. And the fact that we know that means that we can actually use one of our constant acceleration formulas, which is v squared is equal to u squared plus 2as. I believe. Right? Yeah. Because we don't know what our displacement is after that point. So we can go, our final velocity is 0. 0 squared is 0. Our initial velocity is what we found here. Right? Plus 2a. Our a is -9. And then our s is what we're trying to find. Okay, so if I have not stuffed anything up here, this should be the equation that's going to give us our answer. So let's go to our solve, trusty solve. We go 0 is equal to 180 times 400 on 9 minus x, right? Was it? No, it wasn't x, right? No, x is the same thing as s. That's the distance that we're trying to find. So we go to the power of 1/3 plus 2 times -9 is just take 18 times s, or in this case x. And solve for x. Syntax error. Oh, the brackets here. 26.24 or 28. 26.28. And remember here, I used s instead of x, but it makes no difference. I can just, it's the same thing. As long as you're talking about this distance, you should be fine. Okay, so that gave us s is equal to, what was it? 26.28. How many decimal places do I want? 1. So 26.28 is 26.3 meters. So that would be my answer. Hopefully I haven't messed anything up, but yeah, that is pretty tough. A mass of m1 kilograms is placed on a plane inclined at 30 degrees to the horizontal. It is connected by a light inextensible string to a second mass of m2 kilograms that hangs below a frictionless pulley situated at the top end of the incline over which the string passes. Given that the inclined plane is smooth, find the relationship between m1 and m2 if the mass m1 moves down the plane at constant speed. Okay, I'm just going to quickly draw the weight force of this. So it's going to be m1g, right? You can form a triangle here. Okay, this angle in there is 30 degrees. This component is m1g sine of 30, okay? And this is pulling down at m2g. All right, now this component is going in that direction, so we have to go m1g sine theta, or sine 30 degrees, take away m2g is equal to mass times acceleration. It's going down at a constant speed, so the acceleration is 0. Okay? Now, sine of 30 is... okay, wait. We also do have tensions here, but the tensions do cancel each other out, so that should be fine. Now, here we have m1g sine of 30 degrees is a half, so we get that. Take m2g is equal to 0. And then now just add this to both sides. We get m1, why do I keep on doing that? m1g on 2 is equal to m2g. You can divide both sides by g's. The g's will cancel and you'll be left with m1 on 2 is equal to m2. And this leaves us with m1 is equal to 2m2. Okay. The masses are now placed on a rough plane inclined at 30 degrees with the light inextensible string passing over a frictionless pulley in the same way, as shown in the diagram above. Let n be the magnitude of the normal force exerted on the mass m1 by the plane. A resistance force of magnitude lambda n acts on and opposes the motion of the mass m1. The mass m1 moves up the plane. Mark and label all forces acting on this mass on the diagram above. Okay, so let's get rid of our graffitiing from before. Now, we do have our normal force. Let's call this normal force n, like they've given us. It's moving up the plane, right? So that means our friction is going to be working in the opposite direction. And our friction had the magnitude of lambda n, right? We still have our downwards force of m1g. Why do I do that? m1g. We have our tension here, and then our m2g as well. Okay. That looks about right, if I haven't missed anything. Yeah, it looks good. Taking the direction up the plane as positive, find the acceleration of the mass m1 in terms of m1, m2, and lambda. Okay, so what I'm going to do now is, let's actually break down this component into its horizontal and vertical components. Right angle triangle. This is the same angle as what we have here, 30 degrees. This becomes m1g sine of 30. Sine of 30 is a half, so I'm not going to write that. I'm just going to write this. This component here is m1g, stop doing I, m1g cos of 30 degrees. Cos of 30 degrees is root 3 on 2. So I'm not going to write cos of 30, I'm going to write root 3 on 2. Okay, now that we have that, let's work out all of the forces working in their particular direction. So taking up direction up the plane is positive. Okay, so we have m2g, right? That's what's working here. m2g. These have to be equal. They cancel each other out, right? m2g is the only one pulling it up the plane or in this direction, right? Then working in the opposite direction is going to be our m1g on 2 there. And we also have lambda n working opposite direction as well. Now the thing with lambda m is this. We know that n and this vertical component need to cancel out, right? Because the mass isn't going through the plane, is it? So we need to have n is equal to m1g root 3 on 2. Okay, n is equal to this vertical component. That leaves us with the friction force being a lambda m1g root 3 on 2. Okay, so that's what our friction force is. So coming down here, instead of lambda n, I'm just going to write what we have here. Now these are all the forces that are influencing the motion of m1. Okay, the tensions cancel out. We have the m2 pulling the m1 up the plane, and we have the friction working against it, and the horizontal component working against it as well. And this is equal to ma. The mass of the entire system is going to be both of the masses added together. This is because the whole thing acts as one system. The string is inextensible, and that means that they're both going to be affected by the same weight, both m1 and m2. So the whole system's weight is m1, m2, it's the mass of the whole system, and then we have acceleration. Okay, now let's kind of clean up this left-hand side. I'm just going to multiply this by 2 and 2. That leaves us with, let's write it in black, 2m2g, take m1g, take lambda m1g root 3 on 2. Oh no, not on 2. It is on 2, but we're also dividing this across, so we're going to have m1 plus m2 all equal to a. Now, just to clean it up a tiny bit more, let's factor out g from the top. 2m2, take m1, take lambda m1 root 3 all on 2 m1 plus m2 is equal to a. Okay, that's looking good. Sometime after the masses have begun to move, the mass m2 hits the ground at 4.5 meters per second and the string becomes slack. At this instant, the mass m1 is at point P on the plane, which is 2 meters from the pulley. Take the value of lambda to be 0.1. How far from point P does the mass m1 travel before it starts to slide back down the plane? Okay, so this sounds like a constant acceleration problem. So using this formula here, right? Remember, before it was all one system, right? So once m2 hits the ground, m2's mass isn't affecting the acceleration of m1 anymore. So we can take m2's acceleration to actually be 0. Not acceleration, the m2's mass to be 0. So using this acceleration formula here, we can say that since m2 hit the ground, right, we can say that M2's mass is 0. So wherever we see an M2, we can put a 0, and that's going to leave us with acceleration is equal to negative M1, take lambda M1, root 3 on 2M1, okay, is equal to A. Now, as you can see, we can factor out M1 from the top. That's going to leave us with G at the front, negative 1, take I keep on saying the same thing, lambda, root 3 on this is equal to A. Now, from here, these two cancel. So we actually have a constant for our acceleration, which is really good. So coming back up here, our acceleration is equal to G, negative 1, take lambda. Remember, it says here lambda 0.1. Okay. On 2. Okay, very good. Now, our initial velocity, right, is going to be that, because before it hits the ground, it's connected. So our initial velocity is going to be the same as M2. Okay. Okay. Our final velocity is going to be 0, right? Because when it moves up the plane, there's going to be a point where it just doesn't have enough motion to go up anymore, and then it starts going back down again. So our final velocity is going to be 0. Now we can use our formula for constant acceleration and go v squared is equal to u squared plus 2as. We want to actually work out what the displacement is before it starts to slide back down. So we go 0 is equal to 4.5 squared plus 2a. That is this mess here. I'm not going to write it down, I'll just write a, right? And it's times s. Now, if we just go on the calculator and just solve for what s is, that should tell us how much it's going to slide up, okay? So let's go to solve. 0 is equal to 4.5 squared plus 2 times a. Now, a I didn't write down. Okay. So it's 9.8 instead of g times negative 1 take 0.1 times root 3 on 2. Hopefully I didn't mess that up. And then we go times s, or x in this case, it doesn't matter, and then solve for x. 1.76. 1.76. So we go s is equal to 1.76 meters. So that would be my answer. Okay, find the time taken from when the string becomes slack for the mass m1 to return to point P. Okay, give your answer correct to the nearest tenth of a second. Okay, so what I would do is, let's actually just draw some nice little diagrams here. So we've got two phases actually, right? We got phase 1. Phase 1. Our thing looks like this. Now I'm going to ignore the mass 2 because right now the string is slack. Now, from point P, right, this is P, our mass is going to move up a certain amount, right? And remember, we just said that it moves up 1.76. So it needs to go up 1.76. And that's going to take a certain amount of time, right? And after that 1.76, it's going to start going back down. So that's when our phase 2 comes in. Phase 2. Okay, at phase 2, our box or our mass is up here, right? And it's going to go back down to point P. Okay, so those are the two times that we need to find. And in phase 2, our friction is actually going to be working in the opposite direction. So our lambda, or our friction component, is going to just switch signs. Okay, we've been dealing with it here. Right, all we're going to do is just make that switch signs later on. Okay, so for phase 1, let's deal with that first. Phase 1. Okay. Now for phase 1, what do we have? We have our displacement. we have our final velocity being 0 because it needs to move up and then it's going to go back down. Our initial velocity was 4.5, right? 4.5, yep. And what else do we know? That's about it, right? Yeah. So we can use our constant acceleration formula of v is equal to u. Oh, wait, and we also knew our acceleration. Our acceleration was up here. We can use v is equal to u plus at, right? And we can go 0 is equal to 4.5 plus our acceleration, which was this mess. I'm actually just going to copy it. Okay, it was that mess, and we also have times t. Okay, now solving for time here will tell us how long it takes for the mass to actually go up the 1.76 centimeters or whatever it was. Okay, so let's go to our calculator and we go solve. We can go 0 is equal to 4.5 plus our acceleration, which was right here. I'm not going to write the whole thing again. Right, and it was times t, or we can use x. 0.7827. Okay, so that's our time, right? Now, that's how long it takes for phase 1. Now we actually need to work out phase 2 as well. So phase 2, let's use a different color. Phase 2. Now, in phase 2, okay, in phase 2, our final velocity, or our initial velocity is 0. Our initial velocity is 0. Our acceleration is going to be this, but with this direction of our friction component being reversed. So that's going to be a plus now, I believe. If I'm not mistaken, this should work. So our acceleration is going to be g minus 1 plus 0.1 root 3, because now that it's moving down the plane, right, all of our forces, right, or our friction force is going to be going in the opposite direction. Okay, so that's the main difference there. So acceleration is that, okay, and then our displacement is what we knew from before, right, 1.76. So I believe we can use the equation s is equal to ut plus half at squared, if I'm not mistaken. And then we go 1.76 is equal to u times t is 0 plus a half a, which is what we have here, a t squared. Okay, hopefully this is right. Hopefully I haven't messed anything up. And this should give us how long it takes for phase 2. 1.76 is equal to a half times our acceleration. Now remember, we changed the signs of our friction. Okay. Times x squared plus x. What have I messed up here? I think it was the fact that I switched the friction like that. That may be what I messed up. Let's actually just consider this whole thing again. Let's just look at the forces acting on it now and work out the acceleration naturally. So in the opposite direction, right, we still have... What have I messed up from here? Remember, this was taking direction up the plane as positive, right? So, as positive. So it does make sense that I make that part positive, right? Because initially our friction, right, it's going down that way. So that's negative, right? But the fact that we're going down the plane and the friction is working upwards, that should mean the friction is positive still, or the friction is positive now. Okay, so that does make sense logically, but what's not making sense here? It might be the fact that I used a rounded figure here. Right, I used a rounded figure there. So let's go here, solve for this. Is that a possibility? Syntax? No. False still. Oh, I'm bad. I think no. Is it because I wrote this equation wrong? Is this minus? I think that's why. I think I wrote down the equation wrong. I think that's minus. Actually, let's just have a look. Let's just have a look at this. Constant acceleration formulas. You'd have this on your formula sheet as well, so make sure you know them really well. Let's go to our constant acceleration formulas. Wait, here. Okay, we got that. Okay, no, it was right the first time I wrote it. Wait, I'm pretty sure it's something to do with the signs that I'm messing up. Let's go to our calculator again. Paste this. Negative 4.05. Yep. Oh, that's why. Okay, no. Our formula was correct, okay? The main issue is, since we're going down the plane now, our displacement needs to be negative. Yeah, it gives the same answer. Okay, that was the main conceptual error there. Okay, so the equation itself was actually right. It was the fact that in phase 2, right, remember, we took direction up as positive. So if we went up plus 1.76, if we're going down, it needs to be negative 1.76. So that was the main issue there. Okay, that makes sense. Now, that leaves us with t is equal to 0.932. Oops, let's go back. Now, all we need to do is to get the actual time taken is just add both of these up together. Okay, so we go total time is equal to 0.78 ... plus 0.93 ... And that gives us, using all the values in here, plus, oops, let's go back to our time up here, 1.7, because it says the nearest tenth. So my answer here would be 1.7 seconds. Okay, that was definitely tough. You do need to be very meticulous when you're doing all of these. You need to make sure your signs aren't messed up, otherwise your answer will be wrong. But still, it is an important skill to be able to look back at your working and really scrutinize everything and see if you made any logical flaws within it. Okay, the maximum load of a lift in a chocolate company's office building is 1,000 kilograms. The masses of employees who use the lift are normally distributed with a mean of 75 kilograms and a standard deviation of 8 kilos. On a particular morning, there are n employees about to use the lift. What is the maximum possible value of n for there to be less than a 1% chance of the lift exceeding the maximum load? Okay, so from this, right, we can tell that the mean is 75 kg. Okay, our standard deviation is going to be our standard deviation for the population over root our sample size. All right, now what I would do is, let's actually just input this, just so we can draw a normal distribution. For these questions, drawing a normal distribution is always helpful. So let's go with our axis here. Normal distribution. Draw that a bit better. No. Come on. Something like that. Okay, our mean is 75, right? Our mean is 75. Now, if we have 1,000 kilos and we have an N number of employees, what's the average mass that each employee can have, right? Let's just think about this with an easier example. If we have 1,000 kilos and we have 10 employees, doesn't it make sense that we can have 1,000 on 10 equals 10, or not 10, equals 100 kilos average per person, right? That makes sense. Now here, on average, we can have 1,000 on N. So that means our value here, 1,000 on N, right, is what we can't exceed if we don't want to exceed the maximum load. Now, it says we want the probability that it exceeds that maximum load to be less than 1%. So we want the area to the right of that to be less than 1%. Now, the thing that will be helpful for us would be to actually standardize this and work out what z-score we would need, or how many standard deviations away we would need in order for that probability there to be actually 0.01. So what I'm going to do is go onto the calculator and do inverse normal. Inverse normal of 0.99. I'm doing 0.99 because the inverse normal function on this calculator reads from left to right. And if there's 1% on the far right, that means there's 99% on the left. That gives us 2.326. So we get, this is 2.326. Z is equal to that. Now, if we want this to be less than 1%, right, would we need to push this z-score outwards this way or leftwards? We would need to actually shrink this area, right? We want it to be less than 1%. So that means, let's actually work out the z-score here. The way you work out the z-score is 1,000 on N minus 75 on our standard deviation. Right, that's how to find that actual z-score, and we want to push it more to the right. So we want it to be bigger than that value. Okay, and remember, the z-score is how many standard deviations away it is, and the way you work it out is the distance from there to there, that's what this is, divided by your standard deviation. Okay, now we have this formula here, or this equation here. If we solve this, this should tell us what N needs to be. So let's go here. Algebra, solve. Right, let's actually just go back. I forgot it. Okay, so that's what that is. Okay, so it's going to be, let's go back here. It was a fraction 1,000 on N. Let's just use X minus 75 on 8 on root X. And this was greater than that z-score that we found. Solve for X. Okay, this tells us that X needs to be in between that. Now, it asked us for the maximum N value. If N needs to be less than 12.45, that means our maximum N value is 12. So we get N is equal to 12. That's our maximum N value. Perfect. Claire, who is one of the employees, likes to have a hot drink after she exits the lift. The time taken for the drink machine to dispense a hot drink is normally distributed with a mean of 2 meters and a standard deviation of 0.5 minutes. Not meters, I said meters. Minutes. 2 minutes and a standard deviation of 0.5 minutes. Times taken to dispense successive hot drinks are independent. Okay. Claire has a meeting at 9 a.m. and at 8:52 a.m. she is fourth in the queue for a hot drink. So, say we got a person, another person, another person, and another person. And this is the special one. This is Claire. Okay. Assume that the waiting time between hot drinks dispensed is negligible and that it takes Claire 0.5 minutes to get from the drink machine to the meeting room. Okay. What is the probability, correct to 4 decimal places, that Claire will get to her meeting room on time? So, from 9 a.m. to 8:52, we got 8 minutes, right? 8 minutes. if it takes her half a minute to get from the drink machine to the meeting room, that means in reality we actually have 7.5 minutes, right? All the coffee and all the waiting needs to be done in 7.5 minutes or less, otherwise she's not going to make it in time. So ideally, what we work out is the probability of our x being less than 7.5. But what's our x? We can say our x is going to be equal to each one of the distributions of each person being added up together, okay? So that means our mean of x is going to be this plus this plus this plus this. So it's going to be 4 times the original mean, which is 4 times 2. That gives us a mean of 8 minutes. Now we can't work out the standard deviation directly, but we can work out the variance. That's going to be 4 times the variance of each one of these. And the variance was, what was it? Where is it at? 0.5 squared. So it's going to be 4 times 0.5 squared. And that means our standard deviation of x is just root 4 times 0.5 squared. Okay. Now, all we need to do is go onto our calculator, right? And just use these parameters, right? Our mean there, our standard deviation there, to work out what this is. And we should get the probability. Okay, this is a nice, simple question. Just got to piece the information together. So let's go to here and let's go normal. Oops, the wrong menu. Let's go to normal CDF. We want it to be less than 7.5, so she can actually make it there on time. The mean is 8, and our standard deviation was root 4 times 0.5 squared. Okay, so that gives us an answer of 0.3085. How many decimal places? 4. So we get, 0.3085. And that would be my answer, okay? Next question. Claire is a statistician for the chocolate company. The number of chocolate bars sold daily is normally distributed with a mean of 60,000 and a standard deviation of 5,000. To increase sales, the company decides to run an advertising campaign. After the campaign, the mean daily sales from 14 randomly selected days was found to be 63,500. Wait a minute, now that says main. Okay, I assume it means mean. That's a typo then. Claire has been asked to investigate whether the advertising campaign was effective, so she decides to perform a one-sided statistical test at the 1% level of significance, write down suitable null and alternative hypotheses for this test. So, our null hypothesis would be our mean equaling 60,000, and our alternative hypothesis would be that the intervention was actually successful and it was greater than 60,000. Okay. Determine the p-value correct to 4 decimal places for this test. Okay. Now, conceptually looking back at what a p-value is the chance, right, or the probability of getting something like this value that we got, or even bigger or more extreme, if our mean is actually 60,000. Okay? So, on a normal curve, let's draw it in. If our mean is 60,000, our p-value, right, since this is a one-sided statistical test, our p-value is going to be the chance of observing something like that or even more extreme, okay? So going on the calculator, we go to normal CDF, and we go, 3,6,500 or more extreme. Given that our mean is actually, did I write it all wrong? I did, didn't I? 63,500. 63,500. Given that our mean is 60k, and our standard deviation, let's work out our standard deviation. Our standard deviation is going to be 5,000 on root n. N is 14 here because there's 14 selected days. So 5,000 on root 14. So it's going to be 5,000 on root 14. 0.0044. Okay. So we get 0.0044. Giving a reason, state whether there is evidence for the success of the advertising campaign. Okay, so from our p-value of 0.0044, we can say that that's less than our level of significance. Now, conceptually going back to what a p-value is, remember, a p-value is the chance of observing something as extreme as what we just got, or even more extreme if our mean is actually 60,000. So if that probability or that p-value is less than our level of significance, that means that the chance of that happening is way too low if our mean was actually 60,000, right? It's saying it's way too low and it could not have happened logically if our mean is 60,000. So that gives us enough evidence to say that in order for this to happen, the mean has to be higher than 60,000 because the chance of it happening if it was 60,000 is way too low. So you say reject HO campaign was successful. Okay? Find the range of values for the mean daily sales of another 14 randomly selected days that would lead to the null hypothesis being rejected when tested at the 1% level of significance. Okay, let's put in our, let's put in our sticky note so we can draw. Now with these questions, as always, I recommend to draw a normal distribution. No, what was that? Okay, okay. Now here we're saying our mean is 60,000. Find the range of values. Okay, null hypothesis being set. Okay, so we're going to have a critical value here, right? And past that value, right, we got the area here. We want it to be rejected, right? So the area past that needs to be less than 0.01. Less than 0.01. Now, that is similar to what we did up here. It's similar to an extent. Okay, so we want the area past that value to be 0.01 or less than 0.01, right? Okay, so let's find the z-score that would let the area to the right of it be less than 0.01, okay? So we go here, inverse normal, and remember it reads it from left to right, so our area would be 0.99, 2.32635. 2.32 blah blah blah. Okay, now all we have to do is actually, this could actually just give us our value straight away. So this, right, instead of using the z-score, right, you could actually just go back here, go to inverse normal, because we know all of our other parameters as well. We can just go, our area is 0.99, our mean is 60,000, and then our standard deviation is 5,000 on root n. So we don't need to do all that work anyway. Okay, the other way of doing it, the z-score way, actually shows you the logistics and how it's actually working. But this is the same process. So this is 63108.7. Okay, so that tells us that this critical value is 63108.7, okay? Now, do we want our values to be less than that or greater than that for this probability to be less than 0.01, right? In order for it to be less than that, it needs to be greater than that, right? We need to move that critical value, or that critical value is there. Our means of our samples that we take need to be past that point. Otherwise, the area to the right of it would be greater than 0.01, and that wouldn't be rejected. So therefore, we say the mean daily sales need to be greater than or equal to 63109, right? Nearest integer. Hopefully I haven't messed anything up. The advertising campaign has been successful to the extent that the mean daily sales is now 63,000. A statistical test is applied at the 5% level of significance. Find the probability that the null hypothesis would be incorrectly accepted based on the sales of another 14 randomly selected days and assuming a standard deviation of 5,000. Okay, so let's bring in our note again. Let's draw it in. Why? Why does that happen? That's not satisfying, is it? Just looks horrible. Okay, that's good enough. 60,000. Okay. Okay. Now, the null hypothesis being accepted, right, is the chance that we get something. Remember, this was our critical value from before. It's the chance that we get something that is... Have I messed anything up? Let's just go back here. Oops. Okay, the chance of accepting the null hypothesis is going to be if we get something that is to the left of this critical value, okay? If we get something that's to the left of that critical value. So, oh no, okay, we can't use 63108.7 because here we were dealing with 1%. Here we're dealing with 5%. Okay, there we go. Let's go back here. This is our critical value, our new critical value. This area here needs to be 0.05 to get that critical value. Let's go to our inverse normal. If that area on the far right is 5%, the area to the left is 95%, our mean is 60,000, and our standard deviation is 5,000 on root 14. 62198. 62198. So our critical value is 62198. Now remember, we accept the null hypothesis if we don't have enough evidence. So we basically need to have our sample mean that is to the left of that critical value, right? Because if we have a sample mean that's to the left, the area to the right of it, or the p-value, is going to be bigger than that level of significance. And that's going to lead us to believe that the chance of getting something that extreme is pretty likely, and therefore the null hypothesis can't be rejected. So what we need to do here is work out the probability of us getting something that's smaller than this, given that our mean in reality is actually 63,000, okay? Because in reality, right, to the eyes of the researchers, they still think that you have a 60,000 as your mean, right? So what we're trying to work out is what's the chance that in the eyes of the researchers, you're going to get a sample mean that's less than that value that gives you a p-value of 0.05, right? Meaning that your p-value will be bigger if your mean is actually 63,000, because that mean is what's going to actually affect all of your probabilities, okay? And remember, your standard deviation is still 5,000 on root 14. Okay, so if I haven't messed anything up, that would be what we need to work out, okay? So let's go to our probability, CDF, 62198. Our mu is 63,000, and our standard deviation is 5,000 on root 14. 0.274 equals 0.274. That would be my answer. Overall, that was a tough exam, I'm not going to lie. Let me know if there was anything in this that you don't understand. Email me in the description below if there's anything that you don't understand as well. I do offer tutoring, and hopefully that was enjoyable. Hopefully that made a bit of sense and a bit of clarity was given. Hopefully I haven't made any mistakes, but yeah, let me know if I have.